going to jump in to talk about the basics. So the question is, why do we have to program? Now you have to, and besides the fact that you all want to pass this particular course and get into the university, why learn programming language at all? In class online, it's a question to us, it's a conversation. Why do we think we need to learn programming languages?
Create softwares that can help our lives or can make our lives easier.
To create softwares to make our life easier. Yeah, pretty much wraps up the whole thing, isn't it? One computer speak one language, human beings speak another language. Digital world, which is a one or zero, so computers speak ones and zeros. I don't know about you, but it's quite difficult for me to learn a lot of numbers. You can see how much I'm struggling with names, right? Isam, I've said Isan. Yeah, now if you've got it, so remembering a sequence of numbers can be quite daunting, right? So we say we abstract things in a way that is close to what human beings understand. So we can write it, and then of course the computer will take care of the rest and eventually put it in ones and zeros, so the computer will be able to do what we want it to do. Okay, so if you try to play an audio file on your computer, for example, you expect it to work, but that's some code someone has written somewhere working on a certain hardware to eventually output the audio into the analog world, digital ones and zero, analog continuous in time. So far, so good, right? Okay, so we can go into slide at a time, and of course, computers are machines, and they are designed to follow instructions to make our life better, to make the world a better place. But sometimes, actually, they can be so complicated that when you wait till it comes to doing the assignments and other things, just, when you're sweating, you know that it should work. But then that's the thing. Even before we jump into the software side of things, the computer itself is designed by human beings. It's a machine designed by us. Over many years, of course, it's evolved, right? The same way architecture has evolved, the same way, I don't know, making this heater has evolved, and you look at it and you probably think we can have a better heater that can warm the home. This one that's kind of warming only me, right? So things that human beings have designed, and of course it takes people, or now machines designed by people, to ensure the continuity of the design of this hardware. Luckily, almost all of you, even if it's your mobile phone, have a computer before you. If you're online, you are using some form of computing device to access the internet, to actually access this session, right? So this thing that's designed by human beings has the hardware component and then the software component. Yeah? You've got your brain and you've got your thinking that you do. So far, so good. So in order to instruct it to do something, people have to tell it what to do. Or now, AI has to develop to tell it what to do. But even AI is still designed by people. You can have AI designed by AI, but it's also originally designed by someone as well. Hence, to ensure the continuity of making computers powerful on the software side, we need people like you to continue speaking languages or coming up with better programming languages that we can use to interact with the computers. So far, so good. So quiet. So far, so good. Is that a yes or no? Yeah? Or you are wondering, why am I telling you about this? You're wondering? Yeah.
Yes, sir.
Yeah, because at the end of the day, if nobody becomes a software developer, it's going to be quite interesting to continue programming computers, for example. If everybody becomes a user, that's everybody wait for Microsoft Word to be designed, and then use it for typing, then who's actually going to get paid to ensure that version I don't know, version 55 or whatever version of Microsoft Word continue to come out? We need people at the back end who speak the language that the computers can understand eventually, to come up with more powerful software to make the world a better place. We need engineers and computer scientists to continue to move technology to the next level. So we have the hardware designers like myself and Raphael, who's online, who may be probably designing things like Arduinos, Raspberry Pis, but still programming those ones using some hardware descriptive language and other things. And then we have software developers who will be writing efficient softwares to actually control or to develop some things like PowerPoint that we are using at this moment. All the software you see has code behind it. Okay, so we need a programmer who, of course, the program is how we talk to the computers, and we need a programmer who will be talking to the computers. So without programmers, there are no programs, and pretty much computers will be useless. It's just going to be this hardware thing sitting there doing nothing. It's like I bought a robot car, programmable robot car. I'm into robotics. So I bought one 2 years ago. I've never had the time to write a code on it. It's just been sitting there collecting dust, right? Because without the code, it's I don't know, what do you call it? It's just sitting there. It's like worse than a toy. You know what I mean? It can't do anything. Yeah? Right, so we highlighted made of hardware and software. Right, it's just watching the YouTube video, so it should be okay for you. Yeah. So we have the hardware and software codependency. And actually, you walk around a lot with computers in your pocket, the mobile phone. And actually, if you look at the mobile phone, for example, you've got your input, developed a lot. Your input is actually the same as your output device. Yeah, you've got other inputs, so the screen itself is an input device and an output device. And you also have other input devices like the switch on the side. You've got some push button switches, so pushing them. And then this one, in this case, you've got, sorry, that was online. You've got a toggle switch on there. In my case, that sort of mutes the phone. And of course, you've got another input device scanning your face, the camera. And most people will probably have a fingerprint scanner at the back. If you are using Samsung or something like that, and you've got another input device there. You've got an output device, the LED that brights up when you put the flash on. These are most of the common input and output devices, especially when it comes to embedded systems. If the word embedded systems kind of confuse you, think of the Internet of Things. The devices at the end of the Internet of Things, devices that connect to the Internet and are able to send data across the Internet. Yeah. So we have small computing devices. We've got general purpose computing devices. Now mobile phones have become more like general purpose as well, because you can do like word processing and other things on your phone just as you can do on a computer. Okay, so looking at the main hardware basics, I quite like this, but it's quite old. So again, I will switch to this video and then we can have a short chat, right? So we can cover one more slide. So basically, we just want to zoom out into the brain, and then we can see some of the components or how this brain is designed, because it's designed by people. Yeah? All right. So in the brain, have we heard of the control unit? Yes? Yeah? Basically, tell what signal should go where. Easiest way to understand. Control stuff, like the conductor of music, right? Control the flow of the music. Okay. Then we've heard of this wonderful person, arithmetic and logic unit. A computer is a computing device, meaning it's crunching numbers, right? So an example, I'm sure online can see me as well. I'll show you my back to recording as well. Let me do this. An example, if we say we have, we're counting in binary, right? So we have 0, 0 is 0, and then 1 is 1. Yeah? In binary, when you have 1, that is 1. That is 2. 1, 0 is 2. That is 4. Yeah? That is 8. Does it make sense so far? Okay. We're counting in binary. We can have only 0 or 1. Yeah? So if we write a 1, that is just a 1. Okay, the same way if you're counting in decimal, right? The maximum number you can have is 9. You cannot have 10 because it's base 10. So when you move to number 9, you jump to the tens, then it becomes 1, 0. Then you increase the ones until you get to the next one, then it becomes what? 1, 0. But let's go back. So we can have only 0 and then 1. We cannot have 2 because it's base 2. Okay. So in this case, when we have 0 is 0, when we move to 1, because we cannot have 2, we need to move to the next one and it becomes 1, 0. So this is 2 in binary. Yeah? The same way as we keep counting, 4 is divisible by 2. So when it gets to 4, it's going to be 1, 0, 0. 8 is another power of 2, then it's going to be 1, 0, 0, 0. Okay. What you will notice is that I'm shifting 1 by 1 each time. I'm shifting 1 by 1 each time. This is 1. This is 1 times 2. This is 2 times 2. And that is also 2 times 2 times 2. By simply shifting one place, I'm creating a multiplier. Multiplication with the powers of 2. By shifting the 1 backwards, I'm creating division. So just simple manipulation of 1s and 0 can actually create so many powerful things. That is why in the digital world we can do a lot of things just like screen and other things. We simply have to agree when we create something. 100 means maybe sit up or wake up or something like that. The same way that's as far as this particular college is concerned, we have decided that on Tuesday from 9 to 11 we're going to have this particular class, and hence when it's time you turn up. Yeah, the same way colors and other things are represented by a particular sequence that we actually follow. Does this sort of make sense so far? Yeah, so the arithmetic is basically arithmetic logic units. If you look at the brain, inside the brain, there is another powerful device that does all the mathematical manipulations for us, and that's the ALU. Are we satisfied with this so far? Has this sort of formed as a good recap for things that we kind of already know? Still got 5 minutes anyway. Yeah? Okay. A bit more into things. Later you can have a look at this particular, let me point for so those online can see. You can have a look at this particular one in terms of all the stages of it, how the ALU actually interacts with registers. And then that is called the program counter. I mean, I can go over this, but first of all, let's not complicate life for ourselves too much. Let's start with something simple. As we said earlier, you have inputs and then going on into the output. That's for the general computer system. The same way, if you take the processor itself, or if you look at the central processing unit, you've got instructions coming in. Yeah? Going from my memory to my brain, then coming back to either the memory or going to the rest of the body. So you've got instructions coming in and you've got instructions going out, or the results of the instruction going out. So if it's an add, it will be performed in the ALU. If something needs to be fetched from different parts of the CPU, it will go through the control unit to tell what has to be fetched and other things. So it's just basically you get something to crunch and then you crunch it out. Now, if we expand what's going on in the CPU, it's a device, something designed by human beings, okay? So it has a small register, which is like, consider it as a small memory, for example. A small register called the program counter. So if we consider it as a sticky note, but this sticky note has a magic ability to increment itself, for example. So each time we say we look at the sticky notes, then we know what to do next. The same way you look at your timetable and you know where to go for your lesson. So upon reset, the whatever is in this sticky note will point to the first line of code in memory that needs to be executed. Is the address of that line of code. Like you came to this class because you have the address of this particular room. Yeah? Okay. So after the first line increments, then it will just, after it fetches the first line, it will automatically increment itself to the next line. So each time we'll go to the next line of the code that needs to be executed. So that's the program counter, but when it gets that information, it needs to go to the address. So it will put that information on the memory address register. That's the address in memory that needs to go for. And then when it gets the data, it will put it in the memory data register. There is this special register called the instruction register where it does the decoding. And then, of course, you have the accumulator where the results is solved. I know it's just a few key terms. It's just the terms that may or may not be new, but the understanding of how human beings have designed this processor, that is where we want to get to today. Does this make sense to us, or is there any question for those in the classroom or online, or is anybody feeling like, why is this guy explaining this way?